Welcome to Calculus. Today we will investigate finding the average value of a function, taking a look at some logarithmic and trigonometric functions. Our first example is the function f of x equals 2 divided by x, and we're interested in the interval from 1 to 3. So we need to recall what we would use to calculate the average value of a function over a given interval. And that would be given by this expression 1 over b minus a, which are the extremes of the interval, times the integration from a to b of f of x dx. So we want to apply that expression here to find the average value of 2 over x over the interval of 1 to 3. So we'll set it up. The average value is going to be equal to the fraction 1 over 3 minus 1 times the integration from 1 to 3 of 2 over x dx. That's the setup. We're ready to integrate now. I'll simplify this average fraction out front. That'll become 1 over 3 minus 1 is 2, so half. And then the integration of 2 over x is going to be 2 times 1 over x's integration, which is the natural logarithm of x. And we'll evaluate from 1 to 3. Once we've got the integration complete, I want to substitute in my limits of integration. So that's going to be 2 times the natural log of 3 minus 2 times the natural log of 1. But recall, the natural log of 1 is really asking me e to what power would give me 1. That's 0. So that whole second term is going to become 0. And what we're left with is simply going to be half times 2 times the natural log of 3. My half and 2 are going to cancel, and we're just left with the average value of this function is the natural logarithm of 3. So a fairly straightforward example involving the natural logarithm. Let's take a look at an example involving e to the power of x. So here my function is negative e to the power of x, and I'm integrating from negative 3 to 1. We'll set it up for the average value. And again, that's going to equal the fraction 1 over b minus a, so that's going to be 1 minus negative 3 times the integration from negative 3 to 1, for integration from a to b of my function negative e to the power of x dx. Just like in the previous example, we're ready to simplify and integrate. That'll become 1 over 1 plus 3, or 4, so it's a quarter. And then I'm going to integrate negative e to the power of x, and that is itself. Remember, e to the x is its own derivative, therefore it is its own integral, or antiderivative. We're going to evaluate that from negative 3 to 1. So this becomes 1/4. I'm now ready to substitute in my limits of integration. So that's going to be negative e to the power of 1 minus negative e to the power of negative 3. All we've got to do now is reduce down and simplify. So this is now going to be 1/4 times this expression, which I can reduce down to negative e plus e to the power of negative 3. And if that's all multiplying times 1/4, one thing I can do if I don't want a negative power is rewrite this as 1/4 times negative e plus 1 over e to the power of positive 3. I'd like to combine these e expressions. So negative e is equivalent to negative e to the power of 4 over e cubed. That'll give me the same denominator as that 1 over e cubed. And we can finalize and reduce. So that's going to be now negative e to the power of 4 plus 1 over 4e to the power of 3. So that's an example of finding the average value of a base e exponential. We also want to take a look at a couple examples involving trigonometric functions. So here I've got 2 cosecant squared of x, and we're interested in finding its average value from negative 3 pi over 4 to negative pi over 2. Let's apply our average value formula here. So the average value of this function is going to be 1 over the difference in my limits of integration, so it'll be b minus a, so negative pi over 2 minus negative 3 pi over 4 times the integration from negative 3 pi over 4 to negative pi over 2 of 2 cosecant squared x dx. So that's our setup. Let's reduce this fraction first. So this is going to become 1 over negative pi over 2 minus negative 3 pi over 4. I can combine those pi values below. If I call this first one negative 2 pi over 4, and then I'm going to add it to 3 pi over 4. So I can just add my numerators. This is going to be 1 over pi over 4. But then again, I don't really want to call it 1 over pi over 4. I just want to flip that denominator. This is 4 divided by pi. So I'm just going to back up, and we'll call this 4 over pi. Times, now we need to integrate. So the integration of 2 cosecant squared of x. If I think about the antiderivative of just plain old cosecant squared of x, the original function that I would have used to get the antiderivative here would have been cotangent of x. But I got to keep in mind the derivative of cotangent of x would have been negative cosecant squared of x. So if I'm looking for antiderivative with this positive version, it means the original had to be negative. So that gives me a way to integrate here. So that's going to be times negative cotangent of x, and I need to include that multiplier 2 out front. So negative 2 cotangent of x, and that will evaluate from negative 3 pi over 4 up to negative pi over 2. So we've integrated. Now we're ready to plug in my limits of integration. So now what we've got is 4 over pi times negative 2 times cotangent of negative pi over 2 minus negative 2 times cotangent of negative 3 pi over 4. So we do want to evaluate those two cotangent expressions. So remember, cotangent in terms of the unit circle, cotangent is defined as the inverse of tangent. Tangent's y over x, so cotangent will be x over y. The horizontal component divided by the vertical component. So my first expressions here for the angle measured negative pi over 2 So in terms of my values of x and y, cotangent here is going to be 0 because there's no horizontal component over. We would consider that to be -1 for the vertical, but that's going to have the value of 0. So this has the value of 0, which is going to make that whole first term cancel out. Let's also consider on the unit circle this value of -3 pi over 4. So that's going to be in the negative direction, and we'll terminate there. So that's -3 pi over 4. That's one of my 45s. So if I think about that right triangle, it will have the dimensions horizontally -√2/2, same for the vertical. So if I divide the x component by the y component, it's going to be 1. So this has the value of 1. So if I reduce down and simplify, I'm going to have 4 divided by pi. The signs here on the blue expression, negative times negative, will turn positive. 2 times 1, so it's just going to be times 2. That's going to give me 8 divided by pi. And that would be my average value of that function from -3 pi over 4 to -pi over 2. Our last example has the initial appearance of a rational function, but really I just need to recognize this as one of my inverse trigonometric derivatives. So what we'll do is we'll set this up, and then we'll remember what original function has the derivative 1 over 1 plus x squared. But we'll set up for average value. So for this function, that's going to equal 1 over my a and b are, one's very simple, 1, but the a value is square root of 3 over 3. So that's 1 minus square root 3 over 3 times the integration from the square root of 3 over 3 to 1 of this fraction 1 over 1 plus x squared dx. I want to simplify this fraction out front first. So let's just take a moment to reduce that down. So that's going to become 1 over, if I call 1 3 over 3, then I can combine it with the square root of 3 over 3. So that's going to become 1 over 3 minus square root 3 over 3. But then I can multiply by the reciprocal, and it's just going to flip that denominator around, and we'll have the value 3 over 3 minus square root of 3. But then again, I'm not permitted to have an irrational value in the denominator, so I'm going to multiply by the conjugate 3 plus square root of 3 above and below. And that's going to give me 3 times 3 plus square root of 3. In fact, I can actually multiply that out. That's going to be 9 plus 3 times the square root of 3. And then for my denominator, if I do the double distribution, it'll be 9 minus square root of 3 times square root of 3, which is going to be 3. So 9 minus 3 is 6. Remember, with the multiplication of the conjugate, the outer and the inner products will cancel. So that's why I'm not putting anything in terms of square root of 3 for the denominator. And then to finalize here, I can divide a 3 out of all those constant coefficients and get 3 plus 1 times square root of 3 over 2. So that simplifies our fraction there out front. Took some algebra, but we did it. And let's integrate now. So I got to now give my attention to this integrand 1 over 1 plus x squared. And remember, we're seeking the antiderivative for that function. So I want to think, what was the original function that had the derivative 1 over 1 plus x squared? Well, it turns out that that's one of our inverse trigonometric functions. That's the inverse tangent function. So that gives us a way to integrate here. So we'll set that up. So this is the integration of 1 over 1 plus x squared is going to be the inverse tangent of x. And we'll run that from square root of 3 over 3 to 1. So now what we'll do is we'll set this up to plug in my limits of integration. This is going to be equal to 3 plus the square root of 3 over 2 times inverse tangent of 1 minus inverse tangent of square root of 3 over 3. So now we just need to evaluate these inverse tangent values. So remember, what we're looking for is the angle at which tangent has the value of 1. Well, we know that that on the unit circle would be the place where the x and the y component of a right triangle are the same. That's going to be for my 45, or pi over 4. When those are the same and I divide them, it'll equal 1. That's tangent. So the angle that provides that ratio is the angle pi over 4. We also need to think, what's the angle at which tangent would have the value square root of 3 over 3? That one's a little harder to see, but if you recall, my angle here, pi over 6, would have had the dimensions half vertically, square root of 3 over 2 horizontally. So let's just check that the angle, or this ratio for pi over 6, let's see if that is square root of 3 over 3. So I would divide the vertical by the horizontal. So it'd be half over square root of 3 over 2. Then I'm going to multiply by the reciprocal of this denominator to cancel the denominator. And that would give me 1 times 2 over 2 times the square root of 3. 2's cancel, multiply by square root of 3 above and below. And sure enough, that is giving me square root of 3 over 3. So inverse tangent of square root of 3 over 3 is going to be pi over 6. Now we're ready to combine our terms and simplify. So I know for pi over 4 and pi over 6, if I'm subtracting them, I need common denominators. Looks like 12 would do it. So this is going to be 3 pi over 12 minus 2 pi over 12. So that difference is going to be pi over 12. And I'm multiplying that times 3 plus square root of 3 over 2. So we'll set the product there, and then let's merge these two fractions. So it's going to be 3 pi, we'll distribute the pi, plus pi times the square root of 3 over 2 times 12, or 24. And if we were to actually put that in a calculator to get a decimal, it would have the value of about 0.619. So we'll box that. That's our average value. This last example had a lot of algebraic manipulation, but again, the same average value formula we used for our first 3 examples. Well, thank you for joining for these investigations of finding the average value of logarithmic and also trigonometric functions. See you soon.